So let's talk about the magnetic fields created by currents. So a magnetic field is created by a current, and we can use a second formulation of the right-hand rule to find the direction of this magnetic field. So let's say we have a wire, there's a current running through it, and for this second right-hand rule, we take our thumb of our right hand and put it in the direction of the current. And then our fingers curl around that wire in the direction of the magnetic field. So for this particular wire here, my current is running up, my thumb is pointing upward, and so my fingers on this side of the wire are pointing into the ground, okay? And so pointing in, we represent that as an X there, pointing into the ground. And so then my fingers keep on curling around, and on the other side of the wire, my fingers are gonna pop up, pointing up toward me, out of the page, out of the board, out of the concrete. And we represent that as a dot right here. So on this side, the magnetic field is into the board, and on this side, the magnetic field is coming out of the board. So it makes a circle in this direction. That's the direction of the magnetic field around this wire. Now we could take a compass and use it to align it along the direction of that magnetic field, and we'd see the direction of the compass needle change as we move it around this wire to indicate the direction of the magnetic field around this wire here. We have a special law called Amperes Law, which helps us figure out the magnetic field strength at some distance away from our current carrying wire. So let's imagine I've drawn kind of a circle around my wire here. And we can define little length segments along this circle, and each little tiny segment along that circle that I've drawn around this wire here, we can represent that as delta L. And so Amperes Law tells us that the sum of all of the magnetic field that is parallel to this length segment that I could draw around some closed path has to equal a quantity that we call mu sub zero, which is the constant permeability of free space, and times the current running through our wire. Okay. So Amperes Law says that the sum of this magnetic field parallel to this increment delta L that I could draw around some path around that wire has to equal the permeability of free space times the current through our wire. Okay. Now let's assume that this magnetic field here is going to be constant, so we can move it out of this summation. And so then we've got the parallel component of the magnetic field around this path I can draw around the wire has to equal the sum of all those little segments, and then the sum of all of those little segments then would be just the circumference of this circle that I drew here, which would be 2 pi r. So then you could say that this quantity here, the sum of B parallel times the summation of all those little length segments equals B times the circumference of a circle, 2 pi r, where r is the radius of the circle, or the distance that edge of that circle is away from our wire here, okay? And that also equals our quantity mu sub zero times I, okay? So you can set those equal to each other, and if you do that, you see that the magnetic field at some distance away from our wire is equal to mu sub zero times I divided by the circumference of the circle here, 2 pi r, and in this equation, r is the distance that you are away from the center of this wire here. Okay, now let's talk about the magnetic force between two parallel conductors, or in this case we have two wires here, and they have some current running through them. This first wire has a current running parallel to the current in my second wire, and the wires are parallel to each other. So if we use our second right-hand rule, we can figure out where the direction of the magnetic field around these wires. So if I take my thumb and my right hand thumb, point it in the direction of the current here, my fingers point into the ground on this side, so that's going to be an X here. Okay, and then when they curl back around, they're going to be coming out of the ground toward me on this side, okay? So that's the direction of my magnetic field, into the ground here, out of the ground here, so it's circling in this direction. And the same case for this one right here. So the magnetic field, finger pointing in this direction, into the board on this side, out of the board on this side. Cool, so look at what happens here. We've got a magnetic field in one direction, into the board on this side, and then a magnetic field out of the board on that side. And when you have those opposite directions of magnetic field there, you're going to get these wires to attract each other. And so whenever you have current and these wires and this current is in the same direction and parallel to each other, you're actually going to get your wires to attract. Okay? If one of these wires has a current moving in the opposite direction, then you're going to get your wires to repel. Okay? So we can figure out what is the force on one of these wires due to the presence of the magnetic field coming from the other wire right here. Okay, so we're going to figure that out right here. So we're trying to find the force on wire 1, this one here, in the presence of the magnetic field created by wire 2. Okay, so the force on our wire 1 here is going to equal the current of wire 1 here times its length times the magnetic field that it's experiencing. And so that magnetic field is going to be the field coming from the second wire next to it. So that's B2, and then times sine theta, okay? Where theta is the angle between your current and your magnetic field. And these are perpendicular, so sine theta here is going to be sine 90, it's going to be 1. So you can rewrite this as equaling to I times the current in wire 1 times its length times our magnetic field from wire 2. And remember that our magnetic field due to current running through a wire is mu 0 I divided by 2 pi r. So we can replace the magnetic field coming from wire 2 with mu 0 times the current through wire 2 divided by 2 pi r. And in this case, r is going to be the distance between our wires here. So I'm going to replace that r with d. And so when we move down to the next equation, sometimes instead of looking for the force on the wire, we'll talk about the force per unit length, just in case these wires are infinitely long, let's say. And so the force per unit length on this top wire here due to the magnetic field coming from the second wire is going to be equal to mu 0 times I1 times I2 divided by 2 pi times the distance between them, okay? And so that's the force per unit length on this wire, but it's also the same as the force per unit length on this wire, okay? And so the magnitudes of those forces on both of these wires are going to be the same. But the directions will be either pointing in the same direction, either pointing towards each other or pointing away from each other, depending on the direction of the current, and then we have to figure out the direction of the magnetic field from our right-hand rule. And one other important piece of information is that the force between two parallel wires carrying a current is used to define the SI unit of ampere, which we've been using this whole time when we've been talking about current. So to truly define the ampere, if we have two long parallel wires separated 1 meter apart and they carry the same current, and if the magnetic force per unit length on each wire is 2 times 10 to the minus 7 newtons, then that current is defined to be 1 ampere. And so that's how we arrive at the definition for what 1 ampere is, and in order to do that, we have to think about our parallel wires and currents running through them.
Well, let's consider two wires, and they each have a weight per unit length of 1 times 10 to the minus 4 Newton over meters. And our two wires are parallel to each other, and one of them is directly above the other. And so I'm going to assume that these wires carry currents that are equal in magnitude but opposite in direction. So let's say that current for I1 is going in this direction, and then I2 is going off in that direction. So if I think about the direction of the magnetic field that's associated with this current. If I take my hand and use the second right-hand rule, I put my thumb in the direction of the current, and my fingers curl around and tell me the direction of the magnetic field. So if my thumb is pointing in this direction, then I know that on top here, the magnetic field is pointing out of the board toward me. My magnetic field's curling around and it's entering back into the board right here. Now, on my second wire, my thumb is in the direction of the current, and so then my fingers on top are going to be pointing into the board, okay? So into the board is the X. And then they curl around and they exit pointing out of the board towards us, and so that's my dot representation. Okay, so I see that the magnetic fields here, because my currents are in opposite direction, the magnetic fields are repelling each other in between our wires here. So the magnetic field is pointing in the same direction, and so that's a repulsive force here. So if I think about the magnetic force on wire 1, this top one, due to wire 2, the magnetic force, since it's repulsive, is going to be pointing upward in this direction. Now our gravitational force, or our mass times gravity for this top wire, is going to be pointing down here. And so that's its gravitational force, that's its mass times gravity. And so, yes, our wires are separated here 0.1 meter apart, and this top wire just so happens to be magically levitating above the second wire. But it's not magic. We just happen to find just the right orientation, just the right quantities, such that the sum of the magnetic force and the gravitational force acting on this up wire is equal to 0. So our top wire is levitating above our bottom wire here. And so we want to find the current in these wires. And so I mentioned that the current in both of these wires are equal in magnitude but opposite in direction. So we're looking for what is the value of this current that allows us to have this this wire on top levitating above this wire down here. Okay, so we were given the fact that the sum of the magnetic field plus the gravitational field has to equal 0 here. So the sum of our forces equals 0. We're in equilibrium. Okay, so we've got Fg plus Fb has to equal 0. So my gravitational force is going to be minus mg, and then my magnetic force acting on this top wire due to the magnetic field coming from the second wire here, which we just derived in the previous segment when we were outside on the sidewalk. That magnetic force is equal to mu 0 I1 I2 times the length of our wire divided by 2 pi d. And that all has to equal 0. Okay. And d is our distance between these two here. Okay. And then now I'm going to solve for my current. So solve this equation for my current. And I know that I1 has to equal I2. We have the currents on both of these wires are equal in magnitude but opposite in direction. So then I'm going to say that mu 0 I squared, since they're both the same, so I1 times I2, they're both the same, so I can write that as I squared, times L over 2 pi d is equal to mg. Okay, then I'm going to solve this for I squared. I squared is equal to mass times gravity over length times 2 pi d over mu 0. Okay, so I squared is equal to all of this. I can remove that I, or remove the square on the I by square rooting both sides. So I is going to equal to the square root of all this stuff down here. And so you can plug in your value for d, that's the distance between our wires here. L, well, we've got this quantity here, mg over L. The mass times gravity is the weight of our wire. And we are told what the weight per length of our wire is. And so that was 1 times 10 to the minus 4 Newton meters. So you can replace this quantity mg over L with 1 times 10 to the minus 4 Newton meters. Multiply that by 2 pi times the separation between our wires divided by our constant mu sub 0. And whenever you plug in all those quantities, we'll find that the current that has to be the same magnitude running through both of our wires such that the top one levitates is going to be 7.07 amperes.